Now that you know what the problem is about, let's look at some connections, why this is interesting. You've seen an application of range min queries, you just don't know it yet. We've looked in Unit 6, remember the suffix trees and all these things. We looked at the longest common extension problem. So remember that was given a string, or you can read the text, of course. So it was given a string, and then two positions, I and j. You were asking what's the longest part that you can read from these two positions to the right, so that these two are the same before they're stopped by something where they differ. And so the length of this thing, that was the longest common extension. And we've seen that you can use this in the kangaroo algorithm and in other algorithms to speed up certain string problems. At the time, we noted the longest common extension of two positions in a string is the same as the longest common prefix of the suffixes that start at that position. That sounds complicated, but it's just renaming. And we've seen that this, in a suffix tree, like here, you've seen this example. If we take the suffix starting at 1 or in position 5 in banana ban, you will see that their longest common extension, or the longest common prefix, is just the letter A. And you find this length as the string depth of the lowest common ancestor of those two leaves. So again, LCE was the same as LCP of the corresponding suffixes, and we found that as the string depth of the lowest common ancestor of two leaves. Okay? So that's the first step. And then we've seen that there's our magic black box that we didn't look into at the time, that we can find the lowest common ancestor of two vertices in a suffix tree in constant time. And I also promised that we spend linear time for pre-processing, so you can kind of figure out from the Slido question what you would have wanted to answer there. Now that all still doesn't sound like range min queries, right? We've had LCE and LCP and LCA, but no RMQ. And that was because at the time we were talking about suffix trees and only later about suffix arrays. And with suffix arrays, and specifically the LCP arrays, this only makes the connection to range min queries. So we call this the enhanced suffix array, the suffix array plus the LCP array. So here's the two things from back then, just to remind. We have both the suffix array, the leaf array, giving the indices of the leaves in alphabetic order. So these are the starting positions that are stored there, but they're stored in lexicographic order, okay? Which is what you get if you draw the suffix tree and then read the leaf indices off left to right. You remember those pictures? Good, good. I hope so. We had the opposite, which is the rank array, the inverse suffix array, that told you if you want to find the suffix that starts at position 2 in the text, where would you find that in the suffix array? So you would use the rank array at position 2, and that tells you the suffix starting there is the 9th in sorted order. So you can jump down 9th, and then you find it here. That was step 1. So we had suffix array and inverse suffix array to move back and forth between text order and sorted order. And then we added to the suffix array, we added the longest common prefix array. So for any two adjacent suffixes, adjacent in the lexicographic order, we stored how long is the longest common prefix. So here is this array, the red one. Between those two, there's no overlap, so it's a 0. Between these two, it's just A, so it's a 1. And between these two, it's a word of length 3, so the LCP entry is a 3. Okay? It's been a month or so, so I thought it's good to recap that a bit. If you take these two things together, then you can puzzle together this equation for longest common extensions. So we start with my favorite picture, I guess, or text. Two positions, I and j. And would like to know the longest common extension of those positions. We know that this is the longest common prefix of two suffixes, namely the suffixes starting at position I and j in the text. Shall we make this concrete instead of an abstract example? Then you can follow the numbers through. I think this is more helpful. And so we need our string. Don't forget the dollar. Let's pick a somewhat interesting one, right? Let's pick position 1 and position 3 because they have some non-trivial overlap. So we want to know the LCE of 1 and 3. Now the first step is to translate that to longest common prefix of the two suffixes. All right. So we know that somewhere here we can figure out the longest common prefix, but remember the LCP array only stores this prefix for two adjacent suffixes in sorted order. And 1 and 3 happen to be adjacent. Is that too boring an example? Should we do 1 and 7 instead? So I is 1, j is 7. We can find those here manually. They're not adjacent in the lexicographic order, so there's no LCP entry that stores their value. But if we zoom more into this, of course, we can take a look at these, and we find that if these two have something of length 2 in common and these two have something of length 3 in common, the top and bottom row have something of length 2 in common. It's just the shortest shared prefix that you find if you walk from the top to the bottom one. The shortest that is carried through all the time, that's the longest common prefix of 7 and 1. So it should be 2 here. And you might see a connection to range minimum queries now, because we're looking at this LCP array from this position to this position, and we're trying to find the minimum in that range. The minimum is the shortest thing that is equal between adjacent things, and if there's a minimum of 2, then the first two characters have to be equal between any two pairs, and that means they're also equal from the first towards the second. And any longer prefix wouldn't be equal because there's some adjacent pair where they don't match up. Okay? So that's the connection between these two problems. Because we don't have an LCP array entry for every pair of leaves, we use the range min query on the LCP array to get that value, even if it's not explicitly stored. And the rest is puzzling together the right indices. In my example here, I just said, let's try to find the leaves 7 and 1 in the leaf array. You don't want to spend a linear search doing that, and you don't have to. Instead, you know where they start. So you know 1 and 7. So you go to 1 and 7 in the position of the text. You use the rank array to find where in the sorted order they are. And so that gives you at position 2 and 4, you find your two suffixes that you're looking for. That's why we take here the rank array of I and the rank array of j and insert that. And notice that also in this example, even though I was smaller than j, it could happen that r of I is smaller than r of j. That's why in this formula above, you need the minimum and maximum. Good. I think that was the most intricate part for this. This connection is a little following 5 different connections. So it's a little needs a little caffeine to follow through. The good thing is for now, for the rest of this unit, you can forget about this connection if you want. We'll worry about how to find this range-min query efficiently. And that doesn't rely on this connection. But this is one of the prime applications of range-min queries. And because you've seen exactly that, I definitely wanted to make that connection and explain how it works. So to formalize or state again what follows from this example, because we can compute suffix array, inverse suffix array, and LCP array in linear time for a string, we can use any data structure for the RMQ problem. If that has preprocessing time P of n and query time Q of n, we immediately obtain a data structure that has the same time bounds for the longest common extensions. Because the preprocessing time, or maybe I should say formally here plus O of n, right? Suppose the preprocessing time is smaller than linear. We still have to compute suffix array and inverse suffix array and LCP array. So whenever you take some solution for RMQ, you can plug it in and use it for longest common extensions. And you essentially get the same trade-off, unless your preprocessing was boring.